All right, I've handed back the quizzes, and as I mentioned when we took the quiz, we'll probably have another one before the semester's over. This is the second to last week, so we've got this week and next, and I guess what I'm saying is there will be a quiz at some point, and I'd give you more information about that, but I just don't know when I'll remember to give you the quiz, so that's what it boils down to, is my shoddy memory. Homework 15, which is related to this cost estimation stuff we've been covering, that's due on Friday, and we're going to address 2 additional cost estimation techniques today. I've been through maybe about a quarter of the project so far. My initial impression is holding up. Most people did a pretty good job. There are mistakes here or there on assumptions or calculations, but for the most part, it looks like it was a good learning exercise, and so I'm pretty pleased, and I'm going to be working through those as quickly as I can. Any questions related to the announcements before we get into it? All right. Maybe if you've been flying over the country before, you've looked down and you've noticed these beautiful swimming pools. Usually they're next to big cities, often adjacent to a river for some reason. Of course, they're not actually swimming pools. If you jumped in one, you'd know that pretty quickly. These are wastewater treatment plants. And so this is a pretty large one. These basins are aeration basins, and they're shaped in such a way that the wastewater goes through, and underneath the water at the bottom of the tank, there are these diffusing stones, similar to what you'd maybe see in a fish tank. And the purpose of those diffusing stones is to provide oxygen to the bacteria that is in these aeration basins, because the bacteria break down some component of the wastewater that would cause a lot of problems if it got into the river. These circular ones are called clarifiers, and they allow solid particles to settle to the bottom and grease and oily materials to float to the top. And so it's just all a part of cleaning up the water before we discharge it into the river. Now, the reason why I show you this picture is just because this is a relatively large wastewater treatment plant. And we've talked in the past about the idea of getting like a bulk discount on things, when the more you buy of something, the more economical and affordable it may become in order to purchase it on a unit basis. And so, for instance, this large wastewater treatment plant, because they were putting in so many clarifiers and so many aeration basins, probably the per unit cost of construction was quite a bit lower than this much smaller wastewater treatment facility. And probably the same thing is true of all of the consumables that are utilized in this larger wastewater treatment plant. Probably they get a lower cost per ton on chlorine that they're using for disinfection. They probably have a more affordable negotiated electrical rate for the electricity that gets consumed. And a lot of things do get cheaper the more of them that you buy, but not everything. In some cases, there are called diseconomies of scale. And so an economy of scale is when the more you buy, the cheaper it becomes. Can you think of an example in purchasing or construction where making something bigger is actually going to cost more on a unit basis? And I'm not talking on an absolute basis. I'm saying like on the basis of square feet. So if you're building a certain thing, that it actually becomes more costly the larger it is. Can you think of any illustrations of a diseconomy of scale? One that jumped out in my mind is like a high-rise tower. And so the cost of a high-rise tower that's 500 feet tall, thank you. The cost of building a 1,000-foot tall tower is going to be well more than double. It's not going to be that you get a discount because you made it even bigger than before, but because you're having to add additional structural reinforcement to the lower layers in order to support the upper layers. It actually becomes exponentially more expensive the taller the building becomes. And so that's an illustration of a diseconomy of scale. Now the way that we can account for that in a quantitative way is with the cost capacity equation. And it allows us to account for the effect of size variation. So think about the things we've done so far. We've talked about how time can be accounted for with indexing. This is saying that size can also be accounted for. That if you have cost data for something that's larger or smaller, you can still use it to project what the cost may be for the project that you're interested in, as long as you know the cost of that original thing and then a ratio of the sizes. And so Q2 and Q1 are related to the relative size of each of the things. And then this, the magic kind of happens in the correlating exponent. And the correlating exponent is what tells you whether you're getting a discount or whether you're actually having to pay more based on the increase or decrease in size. So if the x value is less than 1, that's representative of an economy of scale. And that just means that you have a cost advantage for building things that are increasingly large. And so maybe the aeration basin in a wastewater treatment plant would be an example of the cost advantage for a larger size. Anything where you can get the materials cheaper or where you're spreading out fixed costs like mobilization over a greater amount of stuff that's being constructed, you're going to see an economy of scale in that case. If x is greater than 1, then that's a diseconomy of scale. And so for some things, a larger size becomes more expensive. And I've already told you about the example of maybe like a high-rise building. There can be diseconomies of scale for things like aircraft, where the larger they get, the complexity of it means that it's just more and more expensive for the larger size. And occasionally we'll have things for which there's no effect from size, where the cost correlating exponent is 1. So just to give you an illustration of these calculations, let's consider the case of a wastewater treatment plant, and the volumes or the size of a wastewater treatment plant is often quoted in MGD, which stands for million gallons per day. It's not Miller Genuine Draft. Although it's a weird thing, in wastewater treatment plant there is something called mixed liquor. Mixed liquor is the mixture of wastewater and settled sludge off the bottom of a clarifier. And so you really wouldn't want that mixed liquor. All right, so we've got a water treatment plant that we have cost data for. This small wastewater treatment plant, oh, this marker's dead. The small wastewater treatment plant where we know the size of it is it has the ability to treat 0.5 million gallons per day. So Q1 is 0.5 million gallons per day, and the cost of that was $1.7 million. Now we can go to tables and find out the correlating exponent. I think it's, yeah, here we go. So this is just some correlating exponents for a variety of wastewater applications. And so you see, in the case of, if we are going to do this wastewater treatment plant overall, then I'm using the correlating exponent here for the aerobic digester, 0.14. But there's a lot of different possibilities, and you'll notice here we have it greater than 1 for the laboratory. So that's the building where they're analyzing water samples. And then an aerated lagoon has a greater than 1, and so do sludge drying beds. And so those are some rare examples of things that are more expensive the larger you make them. In our case, we're going to use 0.14. So x is 0.14. And so we want to find out what is the cost for some wastewater treatment plant that has a capacity of 2.0 million gallons per day. So C2 is unknown. So all we do is just substitute into the formula. C2 is the cost of item 1, which is 1.7 million, And then the ratio of the sizes, 2.0 mgd divided by 0.5 mgd to the power of 0.14. Now, 2 divided by 0.5, that's 4. And so if it was a linear relationship, then we'd just assume that this new thing we're building is 4 times larger than the other one was. But since we get a discount as the size gets bigger per unit basis, then what that means is that actually the C2 is only 2.06 million. And I had meant to find out what is just the effect of that ratio. And so 4 to the power of 0.14, let's see here. So our ratio of size is 4, and then take it to the 0.14 power, 1.214. So this, 1.214. So that means that you can build a treatment plant that's 4 times the size for only about 21% more money than the smaller one. So we have to be sensitive in engineering to opportunities like this. That if you can increase the size of the thing that you're constructing dramatically for just a marginal cost, then you may be able to provide a much greater factor of safety. You may be able to accommodate future expansion within the service area that's meant to accommodate the wastewater. So that's just an illustration of how we can use the cost capacity equation. All right, so I already showed you this table, and so there are academic resources where maybe textbooks of construction would have cost capacity correlating exponents for a wide range of things. It's not just that they only have this sort of data for an like wastewater treatment plant. They'd have it for a lot of different stuff. But you can also create your own cost capacity equations and find the correlating exponent. Like if you're working for a company and they have cost data for lots of different jobs in the past, then what you could do is, number one, correct for the indexing, so the change in pricing over time, and then create your own scatter plot and solve for X. Okay, I'm going to pause here and give you, let's see, the in-class exercise for today. We've actually got 2 parts, and I'm going to break it up. So we'll do the cost capacity part first, and then I'll break in with a little bit more lecture where we do the factor method in just a moment. All right, so in the case of the aerated lagoon, the one that we know about was 3,320,000. The one that we're going to be building in 2017, I guess I should update the dates on that one. This new one that's going to be built, it's going to be about $12.5 million, because not only is it going to be larger, and you get a penalty for increased size, this is a diseconomy of scale, but also it's being built in the future where costs are higher. So, you know, both of those factors are going to be increasing the cost of this new one that's built. In the case of the blower, you can see the individual component costs there, $733,968. even though it has a correlating exponent that's less than 1, still we're building a thing that's larger. And so the thing that's larger is going to cost more than the thing that's smaller, even if the correlating component is less than 1. And then finally, the cost of the pump means that our total cost of all 3 components together is $13,490,503. And if we want to be accurate to the nearest dollar, remember that you have to keep all the precision in your calculator, and so you wouldn't want to round off to like 3.1, or you wouldn't round off to 1.2, because as soon as you do that, then you're no longer accurate to the nearest dollar. All right, so those are cost-capacity equations combined with, just as a refresher, the idea of indexing pricing over time. Both of those ideas together. Any questions on that in-class example? All right, the other component of what we're talking about today is related to the factor method. And the main idea of the factor method is that sometimes you don't have to know the cost of everything to predict what the cost of the project is going to be. Sometimes you can just scale up the overall cost of the project by knowing the cost of one component of it, a factor. And so it's saying that the total cost of the project is going to be some cost factor multiplied by the cost of major equipment. And one illustration of that is that I think I mentioned that I went over to Dubai for spring break. And there's some really fancy restaurants in Dubai, and there's some great restaurants that aren't fancy, but they're still delicious. And one of the ways to know how much your meal is likely to be when you go into one of those restaurants, all you have to do is open up the menu and look at how much they're charging for water. And if they're charging 3 dirhams for water, which is less than $1, then roughly speaking, the meal as a whole will cost about 30 dirhams, which is, I don't know, like $8.50. But if you walk into a restaurant and look on the menu and they're charging 20 dirhams just for a bottle of water, then you know you're in for an expensive meal. And you don't have to look at the cost of chicken, rice, bread, anything else. You can just kind of get an idea of the scale of the cost by looking at one of the individual components. Now, water isn't a major equipment, but just the idea is that you can use knowledge of one component. So, for example, if you know in the example that we're going to be looking at for the handout, it's saying that a diesel generator has a delivered cost of $975,000, and the cost factor for a concrete pad and operator training, and then we also take into account indirect costs. And so the direct costs are the things that are specifically related to the size of the item that's being put into place and have to be included or delivered in order to put it into service. But remember, from the discussion of indirect costs, that indirect costs are things where it's difficult to say exactly how much of that thing is needed for a certain size piece of equipment or service. And so the indirect costs that I have mentioned several times this semester are things like accounting services, where you don't know exactly how many accountants are needed for a certain thing. And so we recover indirect costs a little bit differently than direct costs are accounted for. So in the in-class exercise, what we're going to do is take a look at this diesel generator, and we know the delivered cost. That's the cost of the equipment itself, but that's not the entirety of the costs for putting it into service. Just the equipment itself is part of it, but then we also have to include the other factors, like the operator training and the concrete pad. So what we're saying is that a concrete pad is usually 39% of the cost of the generator, and the training is usually 16% of the cost of the generator. And that's just based on past experience. And so someone who is in construction may develop those same kind of mental shortcuts when they're going to give a bid on pouring concrete or on yard work. You know, if you have an idea of the square footage of grass that is being clipped, then maybe it would be pretty easy to tell them how much to add edging or how much for the fertilizer and that sort of thing. All right, so on this factor method example, what you need to do is apply this equation where you've been given an indirect cost factor and the direct cost factor for two pieces that are besides the major equipment. So the 1 in this equation is taking into account the cost that's known, in our case the generator, but then you also add the direct cost components as well. All right, so on this example, what we're told is that the generator, the overall project has the cost of the generator itself, a concrete pad, operator training, and then there are some indirect costs probably related to the person who ordered it and the electricity in the building that your company works at, and all those indirect costs that also have to be accounted for whenever some new thing is purchased. And so the total cost is going to be the cost of the generator and the pad and the training. So the generator is 100% of $975,000, and then 39% of that cost will give us the fee for pouring the concrete, 16% of that cost. So cumulatively, the direct cost factor is 1.2, if we add that up, 1.55. And then outside of those brackets, the indirect costs are added separately, and so it's cumulative. You don't just combine the costs together, but the indirect costs are levied on top of all the direct costs. So $1.91 million for that diesel generator being put into service. Any questions from that example? All right, so since we're drawing near to the final exam, I wanted to give you kind of a sneak peek on how I decide which information to include on the final exam. My intention is that the final exam is cumulative, but there's added emphasis on the material that we've covered since the second midterm. And so that means that there's going to be proportionally more points to be earned on the newer material. And so this stuff that we're doing right now, today we did cost capacity equations and the factor method, everything back through budget limitations and uncertainty analysis. This block of information only represents about a third of the course, but on the final exam, probably about 60% of the points, maybe even a little bit more, will come from this newer material. But that still means about 40% of the points is going to come from the older material. And the tests that we've had so far have been pretty small in scope because you only have 50 minutes to take the exam. And so there were a lot of topics that I didn't have a chance to ask you about on the first midterm exam. And frankly, it's been so long, I don't remember what questions was on that first midterm exam. I'll probably take a look at it, though, before I write the final. Because, just for example, if I gave you a question where I asked you to do the annual worth analysis, but I didn't ask you to do future worth analysis, then I might be more likely to ask a future worth analysis question on the final. Likewise, for example, if I gave you an external rate of return problem, but I didn't ask a benefit cost problem, then I'll probably go the direction that I didn't go on the midterm exam. So my suggestion is to go through this list one topic at a time and kind of mark off once you've had a chance to review it, look at the corresponding in-class exercise, take a look at which homework each of those topics fed into, and just kind of refamiliarize yourself with each of the topics. Yeah, the final exam will include Excel questions, and so you'll need to bring your laptop computer for that. I've been reading this book about the importance of sleep, and it's opening my eyes on how amazing like the research is when people are deprived of sleep, like how it limits their mental capacity, how it their ability to break down glucose gets worse. Just everything gets so much worse if you've avoided sleep. So the reason I mention it is I think that you should study a little bit each day for the final, and definitely don't stay up Thursday night to Friday. That's like the worst possible way to study for an exam, is the all-nighter. Yeah.
We have another Excel sheet like where we can write down formulas. Is it on exam sheet?
You mean a formula sheet that you can prepare? Yeah. Yeah. I'll give you the details of like what equation sheet I'm going to provide, and but yes, you will be able to include prepare your own page of notes where you outline maybe procedures of things. But the exam will have two parts. It's going to have concept questions and problem solving. And so on the concept questions, you won't be able to refer to that formula sheet that you prepare. You'll only be able to use that on the second part of the final exam. And just to remind myself what the weighting of the final exam is, let's look at the course weight. So the final exam is 25%. So it's weighted even more heavily than either of the midterms are. All right? Any other questions about the final? All right. So remember, the next assignment you've got, that's due on Friday. I'll see you in class on Wednesday.